We now take a look at a couple of try-me problems. The first one is based on problem 444 in your textbook. We have a system for supporting a rural mailbox. It has the feature that the mailbox can swing about line A if it is subjected to a z-direction force, or a force that has a component in the z-direction. And this will prevent damage to the mailbox and its supporting post. We're given that line A lies in the xy plane and it forms this 5, 12, 13 triangle. We have a 150 Newton force that acts in the minus y direction, and then the 200 Newton force has one of two orientations depending on whether we're looking at problem 444 or 445. I'm going to choose here to look at problem 444 with the 200 Newton force acting in the z direction. So take a moment now and pause this video and resume playing when you're ready to see a solution. So we can write the moment about A as the unit vector along axis A dotted into a moment that is calculated based on a point on the axis A. And there are two possibilities here. We could use RAC or RBC as position vectors from the line of interest to the application of the force. I'm just going to choose the position vector from A to C, so we have RAC crossed into FC. And our unit vector along A, again, we can see from the 5, 12, 13 triangle, this lies in the xy plane, and this is going to be 5/13 in I plus 12/13 in J. And then RAC is RC minus RA, and that is equal to 115I plus 18J centimeters. Our force at C is, in this problem, minus 150J, and then we have plus 200K newtons. So we have all the elements we need here, and I'm going to just plug this into my expression for the mixed triple product and get the results. So the moment about A is going to be based on, first for my components for UA, I have 5/13 and then 12/13 in Y and 0 in Z. And we have 115 and 18 and 0 centimeters for the position vector RAC, and then we have 0 minus 150, 200 newtons for the force. And so we can see here that we won't have any contribution from the last column because we've got that 0 in that position, but we'll have contributions from the first two. We'll have 5/13 times 18 times 200, and then we're going to have a minus 12/13 times 115 times 200, and that'll have units of Newton centimeters, and that turns out to be equal to minus 1.985 times 10 to the fourth Newton centimeters, which I can write as minus 198.5 Newton meters. For our second try-me problem, we're going to look at a pair of companion problems that go with this cart that has a couple of different doors, one rectangular and one triangular door. and we have the coordinates of various key points on those two doors, including points that define hinges. And so we're going to look at both 455 and 456. First one, where 455, where we have a triangular door ABC hinged about BC, and we're given a force Q of a certain size, and we want to determine the moment of Q about the edge BC. And then separately, if we're given a magnitude of the force, in this case Q is equal to 9 pounds, we want to determine the direction in problem 456 in which the force Q should be applied so that its moment about edge BC is made as large as possible. And then we want to determine the value of that moment. Take a moment now to pause the video and try the problems yourself. Resume playing when you're ready to see a solution. So we'll take a look first at problem 455, where Q is given. And what we're going to need to do is define a unit vector that points from, for instance, from B to C. And we can see that that is going to lie in the XZ plane. We'll need a position vector that goes from somewhere on the axis of the hinge to the point of application of the force. We could choose either RBA or RCA to do that. For the solution that I'm going to choose, I'm going to use RBA, and you can always go back after the fact and use RCA and verify that you get the same result either way. So I'm going to evaluate the moment about BC as the unit vector along BC dotted into RBA cross Q. Now we can define the unit vector UBC from the relative position vector RBC as RC minus RB, and if we carry that out, we get minus 24I plus 48K inches. The unit vector along BC is RBC divided by its own magnitude. We could make a note here that we could write RBC as 24 times the vector minus I plus 2K, and that would allow us to write the unit vector as minus 1 over root 5 I plus 2 over root 5 K. RBA is RA minus RB, and that's minus 24I plus 24J inches. And finally, we've already got our expression for Q, so we can put all this into our expression for the moment about BC. Again, I use the mixed triple product. Our components of the unit vector are minus 1 over root 5, 0, and 2 over root 5. Our components for the relative position vector are minus 24, 24, and 0 inches. And then our force vector Q is 1, 4, and 8 pounds. And that gives us, we'll get contributions here from the first and third columns, nothing from the second one. We have a 0 there at the top, so we'll end up with minus 1 over root 5 times 24 times 8. Then again, nothing from the middle column, minus 0 times across, and then plus 2 over root 5. We have minus 24 times 4, then minus another 24, so that ends up being minus 24 times 5. And that result ends up being minus 193.2 inch-pounds. So we defined our unit vector from B to C, and the fact that we get a negative value here tells us that the moment about that line is actually acting from C towards B, and we might be able to get a sense from that from the figure here if we draw a position vector in this direction. I'll choose a different color so it's a little easier to see. If we're crossing this position vector into Q, we're going to go in this direction, and so we'll end up with a moment that's more aligned with this direction, and that projection onto axis BC will be from C towards B instead of the other way around. Okay, so now for problem 456, if we want to select a direction for Q to maximize the moment about the hinged axis, this will occur if Q is applied perpendicular to the plane ABC. So what we need to do is to use a cross product to define a unit vector that's perpendicular to that plane. We have already a unit vector that goes in the direction from B to C. We have our relative position vector from B to A, and we can define a unit vector from B to A as the relative position vector divided by its own magnitude. That ends up being 1 over root 2 I plus 1 over root 2 j. Now those two unit vectors, the unit vector from B to A and the unit vector from B to C, are not necessarily going to be at 90 degrees to one another. So if we want a unit vector for Q that is perpendicular to the plane defined by BA and BC, we can write that as UBA cross UBC divided by the magnitude of that cross. So we'll evaluate UBA cross UBC. This is a vector and not a scalar, so we'll populate our top row with the I, j, and k unit vectors, and we have for UBA minus 1 over root 2, plus 1 over root 2 and 0, and then for UBC we have minus 1 over root 5, 0, and 2 over root 5. That's going to give us, in I, we have a 1 over root 2 times 2 over root 5, and I could write that as the square root of 2 over 5I. We have a minus j times a minus 1 over root 2 times 2 over root 5. That likewise produces a plus square root of 2 over 5j. And then in k, we've got a 0 minus a minus 1 over root 2 times 1 over root 5. And that's going to give us a net plus 1 over root 10k. The magnitude of that cross product is the square root of the sum of the squares. And there we've got 2/5 plus 2/5 plus 1/10. And that ends up giving us square root of 9 over 10, or 3 over root 10. And if we take our cross product and divide it by that magnitude, we get for a unit vector in Q 2/3 I plus 2/3 j plus 1/3 k. Having found this unit vector, we're now prepared to find the moment about BC that goes with a value of Q equal to 9 pounds. And the fact that our unit vector turned out this way makes it quite nice, because we can see we're just going to have 6, 6, and 3 pounds respectively in the I, j, and k direction. So our moment about BC now will be UBC dot RBA cross Q And we'll have for UBC, again, minus 1 over root 5, 0, and 2 over root 5, minus 24, 24, and 0 inches, and now 6, 6, and 3 pounds. And the result there will be minus 1 over root 5 times 24 times 3, which is 72, minus 0, we get nothing from the middle column, and then plus 2 over root 5, minus 144, minus another 144, so minus 288, and that result turns out to be minus 648 over root 5 inch-pounds, which is equal to minus 289.8 inch-pounds.